Welcome students, welcome back to Chemical Technology. The last time we have seen the pulp and paper industry and we have discussed the various aspects about the paper and pulp industry. So in this coming modules we will try to discuss about the very well known industry, that is fermentation industry. So this is very well known since many centuries and man is using this fermentation techniques to produce many products. So the very well known product from the fermentation industry, as we know, is the alcohol. So the alcohol that was produced from the many grains in earlier days, and nowadays the fermentation the technique we are using it industrially, and we are trying to produce the fermented product industrially. So earlier it was the alcohol mainly which was produced by fermentation, but nowadays we can produce the antibiotics, there are many enzymes and other vitamins, many products with the help of fermentation. So fermentation is mainly done by the bacteria, and as we know the bacteria they degrade the organic material. So there are two kinds of bacteria generally we can say, one bacteria which gives us useful products and the one bacteria which can produce the products which are toxic to the human being. So the bacteria which gives useful products for human being, so that we will use, and the bacteria which will create the toxic products, so that we can use for the other purposes and to kill the bacteria. So here if we see in daily life, so the alcohol as we know already, then the bread which we get, it is also the product from fermentation. Then penicillin we use when we have any wound, so that is also the product of fermentation. Then there are many products we are using in home. Then when we want curd from milk, then we add the bacteria, so that bacteria that will convert the milk into the curd. So the lactic acid fermentating bacteria we want there. Then if you see our digestive system, so there are many bacteria which will degrade the complex components into the simpler ones. So the main aim of fermentation is to take the help of bacteria and convert the more complex things into the simpler compounds. So the things which we can't have the synthetically, we can create through the fermentation techniques. So the fermentation is very useful in order to create the products which we can't create synthetically. So many complex reactions occurs in bacteria. So here we can say the bacteria is nothing but a mini reactor, or we can say bacteria is a bioreactor. And the main thing with the bacteria is that they can do this procedure at normal temperature and pressure. So if we can understand how the bacteria are producing the products, then we can control those conditions and we can get those products. So industrially, if you want to have the products, then we have to understand how the bacteria behaves, and if we can understand those things like temperature, then pressure, then pH condition, and the nutrients what they need, and which kind of media we want, then we can produce those products industrially at a very large scale. So in the microbiology or in biochemistry, we are learning those things, and also bacteria we know how they behave. So here we will see what are the fermentation techniques and the products. So here we will not discuss about the bioreactor, but we will mainly discuss what are the products produced, and with one or two products we will see how they are produced industrially with the help of process flow diagrams. So the introduction, if we see, the fermentation of fruits to alcohol was known to primitive man and mainly used for making beverages. Then wider application has been recognized in last century, and life process of microorganisms are useful for synthesis of many chemicals of human interest. So here the alcohol was the main products, and the life cycle of the microorganisms produce many products which are of human interest. So those conditions we can control and we can get those products. Then modern definition of industrial fermentation is any microbial process controlled by human that produces useful products. So here the mainly fermentation is to control bacteria and bacterial processes and to get the desired product. The foundation of understanding fermentation laid by Louis Pasteur. So we have seen the work of Louis Pasteur, and we will see what he has done in the coming slides. He showed that the fermentation takes by microorganisms caused by their life cycle, and knowing life cycle of microorganism helps to have fermentation in controlled and in scientific manner. Then microorganisms use includes bacteria, yeast, molds, feeds on organic material, and they will produce the products in the means organic products. Then by controlling feed, supplying nutrients, microorganisms not only grow but also produces chemical substances having economic value. Then microorganisms which are used in fermentation. So the commonly known are yeast and bacteria that are unicellular. Then yeast is irregular oval shape having about 0.004 to 0.01 millimeter in diameter. Then bacteria less than 0.007 millimeter in diverse shapes. Yeast multiply by budding, whereas bacteria by binary fission. So we have seen the reproduction of yeast and bacteria. Then molds grow by vegetative growth of filaments, and the sporulation is also one kind of the reproduction. So that is mainly in the molds. Then reproduction cycle is less than a minute, hence they can grow very rapidly. So here the growth of bacteria is very rapid. So if we can control all the condition, then the product which we get or the production of the desired products also will be rapid in this case. So here if we say, so this is the cut section of the yeast, and these are the different kinds of bacteria. So in this cell, so the process of fermentation will go, and we will get the desired products. So the nutrients which we are supplying, they will be used by the yeast, they will grow, then they will reproduce, and in their life cycles they will produce the products which are of our use. Bacteria if we see, then there are many shapes like spirillum, bacillus, then cocci, and then vibrio. So the fermentation products what we known. So earlier in 1880, lactic acid produces by fermentation. So Cont to acetone and n-butanol at the time of First World War. Then in 1920 to 40, citric and gluconic acid produced industrially. Then during Second World War, many antibiotics such as penicillin discovered. So in Second World War, there was a need for the curation of wound. So wound was getting easily infected by the bacteria present. So use of antibiotic was seen at that time, and the penicillin was discovered. Then in all alcohol, acetone, butyl alcohol, acetic acid, then hormones, antibiotics, drugs, nutrients, vitamins, dextran, these are produced by the fermentation process. So these are various kind of the products which we can produce synthetically in good manner. So that can be produced by the bacterial the processes, and also at a very efficient manner. So these are the many products which we can see produced by the fermentation. So these will include the food and beverages. Then industrially we can produce these products. Then the antibiotics in pharmaceutical industry, then vitamins, and then enzymes. So these are the various kind of products that is produced by the bacteria, and we can have these processes industrially very well known. So the chemical conversions, so there are the oxidation. So if we see the example, then alcohol to acetic acid. Then reduction reaction, it will include aldehyde to alcohols. Then hydrolysis, the starch to glucose, and esterification, hexose phosphates from hexose and phosphoric acid. So this can be carried out more efficiently by fermentation than a chemical synthesis. So as we already discussed, so this is not easy to do by synthetically, but is very easy by the fermentation if we can control the bacterial growth process. Then reaction are very complex, hence can't be classified, hence fermentation itself as a chemical conversion concept is developed. So these are the prerequisites we should have for the fermentation. So the microorganism should be capable of maintaining biological uniformity, thereby giving predictable yields. So here one thing is that there are many reactions occurring in microorganisms. So there are hundreds and hundreds of reactions going in, but we want a specific reaction that will yield the desired products. So we have to see what are the conditions that are needed to produce those products, and we can mimic those conditions, and we can let the bacteria to go by that procedure and to yield the specific products. So here the yield, or we can say the predictable yield, we can have if we know what are the reactions occur in bacteria. Then economical raw material for the substrate. So here also the raw material which are supplying, it should be cheaper, so that we can what are the products we can get, we can sell at a higher rate. So suppose the raw material is expensive, then we can't have the economics for this process. So we have to always look for the raw material on which the bacteria will grow and it will produce the desired products. So there are the many things are going on to find out the raw material or the cheaper raw material on which bacteria can grow and will yield the desired product. Then we should have the acceptable yields. It should not happen that bacteria is eating the nutrients but they are not producing the desired product. So here the yield given by the bacteria should be same. So if there are more than one bacteria which are producing the same products, so we have to look for the bacteria which can use the raw material which is cheap in nature and which can have the high yield. So that bacteria we can use industrially. Then it should give the rapid fermentation, means the life cycle it should be of the shorter time so that we can get the product of the high volume. Then the product that is readily recovered and the purified. So the product which are forming, it should be easily recovered and it can be easily purified. Suppose it is forming more than one product, then it is very difficult to purify it. So here the bacteria, the product which are forming, it should secrete out so that we can recover them readily. Or if the product is forming inside the cell, then it should be easy to break the cells and recover the product back. So these things should be necessary in the fermentation techniques. Then what are the factors that will affect the bacteria? So here the first thing is the microorganisms. So here the microorganisms, so in fermentation we should have the microorganisms which will give the desired products. If there are more than one microorganism over there, or suppose the raw material is contaminated, then many other bacteria may introduce into this. The microorganisms which are using, it's weak or it is not producing the desired products, then that will be the waste. So here we have to take almost care that we are choosing the correct bacteria. Also the things which mean the equipments or the raw material, it should be very well sterilized so that the contamination by other bacteria is avoided. Then you have to take care of the equipment. So here the equipment plays a crucial role because the things which are maintaining, it will depend upon the equipment. So equipment should be such that it can easily control the pH, it can easily control the stirring rate, it can easily control the temperature which is building up in the fermentation reaction. Then we have to look for the good fermentation process that will yield the good yield, and the process should be also simpler one. Then pH is the thing which you have to maintain correctly, because if the pH changes, then bacteria may become inactive and they may not produce the desired product. Then the temperature, again the pH and temperature, these are the most critical things we have to maintain. If suppose temperature is lower, then bacteria will become inactive, and if suppose temperature is exceeding, then bacteria may die in this process. So the temperature and pH we have to maintain. Generally the temperature for which the bacteria will go, so that is around 37 degrees centigrade. So we have to look for, suppose the fermentation plant is in the cold country, then we should have the arrangement for the heating the fermentation. Or suppose the temperature is higher in the region, then we have to go for the cooling and then maintain the temperature. For pH we should have the buffers which will not affect the process. Then aeration and agitation. So here suppose bacteria is aerobic, then we have to supply the oxygen. So here the agitation and the aeration, it should be good. Otherwise it will lead to the suffocation and the bacteria may die. And also agitation rate should be such that it should not kill the bacterial cells. So agitation we have to keep in such that the mass transfer is also higher, but at the same time it should not damage the bacterial cell. Then pure culture fermentation. So here also again we have to see the same thing, that the culture we are using, it should be strong and it should be pure culture. Then uniformity of the yields. So bacteria, it should behave in uniformly and it will yield the same products throughout the batches. Then what are the major engineering problem in the fermentation? So first thing is the kinetics of submerged and aerobic fermentation. So here is gas liquid contact, because it is aerobic fermentation. So you have to always look for the gas liquid contact. So the mass transfer you have to look in this case. So oxygen transfer between gas bubbles and the liquid. So here the oxygen transfer should be good in this case, so that it will go to the bacterial cell and it can have the reactions over there. Then the liquid to solid transfer should be good. Then the reaction of oxygen and substrate in the presence of microorganisms. So that we can give by the equation that rate is nothing but kg pi y gas minus the y liquid. So here the pi represents the total gas pressure, then y will represent the equivalent mole fraction of oxygen based on the gas phase, and the kg will be the overall mass transfer rate. So we have to increase the mass transfer rate. So suppose y gas and y liquid means here the equivalent mole fraction of oxygen. So in the gaseous phase it should be more, so that it can give the good aeration and it will yield the more mass transfer rate. And if we can increase the mass transfer rate and the total gas pressure, we can have the more rate. So the rate is directly proportional to the overall gas pressure, then overall mass transfer rate, and the difference between the mole fraction between the gaseous phase and the liquid phase. So here if you see, the kg is varies by the PV raised to 1 by 3, where PV is nothing but the mixing power per unit volume, and typical result for fermentation production rates are graphed below for the fixed value of y gas minus y liquid at a given temperature. So here if you see, if the y-axis represents the production rate kg product per kiloliter per hour, and the x-axis represents kg pi or PV raised to 1 by 3. So here if you see, it will increase at certain level and after that it will decrease. So the decrease means represent the cell death. So here the fall of the rate in high kg or high PV value is caused by the rupture of the cell walls of the microorganism under high shear stresses developed in mixing. So we discussed already that the mixing rate should not be very high. So to have the efficient mass transfer rate, we should have the good stirring. But the stirring also should not be high that it will break the bacterial cells. So up to the certain level, it will show the rise in the mass transfer rate and the overall rate. But after that, when the rate is so high, it will break the bacterial cell wall and the rate will then go down. So we have to operate, or we have to keep the stirring power up to this level, and for that one we have to initially go for the pilot plant, and then we have to see what is the optimum value, and then in the further fermentation batch we have to keep this or below this. We should not exceed this, otherwise the rate will fall down very rapidly. And the same thing, so, the other thing involved is rate step involved, the microorganism metabolism rate. The specific rate constant K is defined by, so rate is defined by K, N and Y liquid. So here it is directly proportional to N. So suppose N is on the X axis and the K, which is the rate, specific rate constant on the Y axis. So you can see it will increase. And the K max here, we will always try to achieve the K max. So that you will learn in biochemical engineering in your further course. What does it mean? So the Newton concentration N at optimum mass transfer value is pinched. So Newton concentration increases, then we can have the good rate constant. So we have to look for the Newton concentration that we are feeding, and also that Newton concentration at optimum mass transfer rate, so that bacteria can with very less concentration of nutrient can give the high the yield of the products. Then scale up of submerged fermentation. So here, if the volume of air per unit volume of liquid per unit time V is the constant scale up factor, then severe foaming may result in tank design of the total volume V, where height diameter ratio is kept constant. So here the scale up factor, it is important here, otherwise foaming will occur and the foaming will take the volume. Also the foaming will decrease the mass transfer and we can get the desired rate. So here the height to diameter ratio should be mentioned. So V varies as hd square or as d cube. So X is the escape area for unused gas, varies at d square. So escape velocity we can give by small v into capital E by the X. It is proportional to d cube or d cube by d square or d. So escape velocity increases with the tank size, and H to D is usually between 2:1 or 3:1. So always if you see the fermentation tank, so there is always the kept space is kept between. So the unused gases which will go, otherwise it will build the pressure and it will affect the fermentation very badly. So here the ratio is generally is 2:1, means suppose height to diameter is 2:1. So height is almost double to the diameter of the tank. So generally if you see the shape of this, so it is always the cylindrical size. Then air sterilization and adiabatic compression at 200 degrees centigrade. So air sterilization, so air which you are passing into the fermentation tank, it should be very well sterilized. If you are not sterilizing, then other bacteria may enter into the fermentating media, and it may feed on that, and the whatever the desired product, that won't be created. Also the bacteria which are producing, it will also be harmful of that one. So to sterilize the air, we should have the adiabatic compressor around 200 degrees centigrade. So that will assure us that the air is completely sterilized. Then also the media should be sterilized. So generally this is done in autoclave, and at high pressure and high temperature we can sterilize the media. But the sterilization technique should be such that the media should not be decomposed at that pressure and temperature. Then we have to look for whether we should go for the continuous or we should go for the batch fermentation. So generally the many fermentation processes, they are batch wise, and very few are continuous fermentation techniques. So you have to look for the production whether we should go for the continuous or batch wise. Then design principle for the sterile operation. So here no direct connection between sterile and non-sterile parts. If there is connection, then it may happen that the sterile part may get contaminated with the non-sterile parts. Then all welded smooth inside the construction. Then smooth joint using Teflon or KLF as a sealant gasket. Then use of KLF diaphragm valves. Then independently sterilize each part of the system. So sterilization, we have to always be careful, because sterilization will avoid the foreign bacteria to enter into the fermentation the tank. In the product discussed under this fermentation industry are the industrial alcohol. Mainly in this one we will discuss ethyl alcohol or ethanol. Then we will discuss in shortly about beer, then wines and the liquors. Then we will discuss about the butyl alcohol and acetone. Then vinegar and acetic acid, citric acid, lactic acid, enzymes and miscellaneous compounds. So in this one we will discuss the process flow diagram for industrial alcohol and the beers, and how the beers is produced. Others we will discuss how they are produced and what are their uses. So we will discuss about the ethyl alcohol now. So the molecular weight is 46.07, then density about 0.791 at 20 degrees centigrade. Then there is another characteristics we haven't discussed earlier, that is exposure limit. So it is the percentage of the ethyl alcohol in the air. So it is lower limit is 3.5% by volume and upper limit is 19%. So in explosive limit means at this concentration it may be very explosive. Then toxicity is 1000 ppm. So suppose ethyl alcohol is present in this or above this one, then it will lead to the lethal. And we have the grades as anhydrous, means without water, or we can have the 95% denatured alcohol. Then if we see the end uses of ethanol, then it is used for synthetic rubber preparation, then it can be used as solvent, then preparation of polyethylene, then potable spirit, plastic, acetaldehyde, acetic acid, then butyl acetate and other chemicals. So the main use of the ethyl alcohol is as a solvent. Then method of production. So here there are two kinds of method of production. One is fermentation, another is petroleum processing. So under fermentation, it is from sucrose substrate, then it is from waste sulfide substrate of paper mills that we have seen in paper and pulp industry. Then it is from starch substrate from the starch industry. And if you see the petroleum, it is catalytic hydration of ethylene, then esterification and hydrolysis of ethylene, then oxidation of petroleum. So in this one, we will mainly deal with the fermentation, and we will use sucrose paper of the starch for the production of ethanol. So if you see the reaction, it is we already known. So here we are using the sucrose as a substance, and then we can have the enzyme invertase, which we can give the carbohydrates, and that can be fermented into the ethanol. So here the enzyme invertase to invert this sucrose into the normal sugars, and the normal sugar is fermented into the ethanol with the help of enzyme zymase. So this is the exothermic reaction, and it will evolve the heat. So in fermentation we have to keep the arrangement for the cooling. So the temperature which is appearing in the fermentation, we should remove it with the help of cooling. The side reaction may happen that the high molecular weight alcohols or the aldehyde, that may increase. So that together these kind of products, so together that will be named as the fusellyl. So if you see the reaction mechanism, so as far as the biochemistry is considered, then ethanol is produced by the glucose. So glucose, so the 2 ADP into 2 ATP. So here the NAD they will reduce and they will oxidize simultaneously, and they will give the energy to this process. So glucose is first converted into the 2-pyruvate. So always the 2-pyruvate is the basic chemical that will lead to the further products. So in this case ethanol products. So any fermentation, if you see from the glucose, you will find always 2-pyruvic acid is forming over there, and it will lead, the energy will be given out over here. Then after the evolution of CO2 from the pyruvate, so CO2 when involved, then we can see CH3CO, which can be reduced to the alcohol. So CO2 is removed, then we can have the acetaldehyde. So 2 acetaldehyde will be formed, and with the help of the reduction we can have the ethanol. So in this one, the ADP will be energized to 2 ATP, and NAD, here the H will be given to reduce this one. So nicotinamide, here it will be the H will be given out to the acetaldehyde, and it will give the aldehyde. So here the fermentation regenerates the NAD plus for the glycolysis. So here the H will be utilized and H will be generated here. So the NAD plus it will be generated. So this process will continue. So this is mainly happens in the yeast cells. So here the CO2 which is evolved, it is the decarboxylation reaction. In the fermentation, we can see the tiny bubbles which are appearing. So they will contain the CO2 gas. So the agitation is required to remove the CO2 gas accumulated in the fermentation. Otherwise, it will lead to the lifting of the mass. And also CO2 is the gas which can hold the heat. So it can build the heat in the fermentating mass. So we have to always take care of the CO2 removal from the fermentating mass. So here if you see the quantitative requirement, so if you are producing 100% alcohol, then we will require the molasses as the raw material, then sulfuric acid, ammonium sulfate, then coal for energy, then process water, cooling water, then electricity for the stirring, then byproducts which is removed from this, and fusellyl, that is acetaldehyde and other components which are of now not the main products, then cattle feed or the fertilizer, and the plant capacity will vary from 10 to 100 tons a day. So the process description, so here is directed to 10 to 15% of sugar concentration, and pH is maintained acidic, that is 4 to 5. Then nutrients for the bacteria or the yeast we require are the ammonium and magnesium sulfate or the phosphates. Then dilute mixture called the mash is run into the large wooden or steel fermentation tanks. So nowadays, earlier it was the wooden tanks that we are using, but nowadays at industrially we use the large steel fermentating tank. Then yeast is added in sterilized mash and heat is removed by cooling coils. And temperature is maintained around 20 to 30 degrees centigrade, and the time required is around 30 to 70 degree hours for the fermentation. Then the exothermic reaction, it will lead to temperature rise of 35 degrees centigrade, and the CO2 evolved is removed by water scrubbing and compressing, or it is vented out. So here the mash is taken, then diluted, the nutrients are added, both are sterilized, and then yeast is added. Then yeast is allowed to fermentate, then the 30 to 70 hours, and this temperature and pH of 4 to 5 will give the products, and what are the byproducts that will be scrubbed out or vented out. Then the separation of the 8 to 10% alcohol which is formed in the fermentation liquor is called the beer, which is accomplished by a series of distillation. In the beer still alcohol 50 to 60% concentrate, and the undesirable volatiles such as aldehydes are taken off at the top, fed to the aldehyde still, and the alcohol is pulled off as a side stream split into the rectifying column. An azeotropic mixture which is alcohol and water 95% is taken off as a top side stream, condensed and run into the storage where it is split into the three as a direct sale as a potable or government control alcohol, or it may be denatured by small addition of mildly toxic ingredients and sold for industrial uses, and made anhydrous by ternary azeotropic distillation using benzene or extra distillation using ethylene glycol. So here what happens, we can use that, we can send as diluted, or we can denatured, and we can as a dilute toxic. So toxic, generally the methanol is added, or if you want to have the more concentrated ethanol alcohol, then we can go for the distillation. So here the azeotropic mixture of water and ethanol, it is very difficult to separate. So we will use the benzene or extractive distillation techniques to separate them, and we can have the higher grade of alcohols. Then fusel oils drawn up from the bottom and separated by the decantation, and this is sold directly for the solvent or fractionated to yield amyl alcohol predominantly. So this is the ethyl alcohol by the fermentation. So the basic raw material is here the molasses, which contain the sugar. So here the molasses is taken. Then first thing is we have to sterilize them, and then we have to add the nutrients over there. So they will be taken and they will be sterilized. And then nutrients, they will be added to the fermentation tanks. So here after the sterilization, so the nutrients which are added over here, then CO2 is removed, then yeast culture is added over here, then yeast storage over here, then fermentation tank. So the molasses after sterilization will come here. In the fermentation process, CO2 will be evolved, that is taken out, and the yeast which will give the alcohol. So here the molasses first may be sterilized, or it may be diluted over here. So molasses, suppose concentration is not the of desired level, then we can add the water and we can have the desired concentration. So here the diluted molasses, that will come to fermentation tank and we will give the alcohol, or they can we can have the yeast over here and we can have the alcohol, and the CO2 will be evolved. So in the both the tanks, it is directly added molasses, or here the diluted molasses, both will give the alcohol and they will evolve the CO2, which can be scrubbed out. Then that the alcohol which is produced is called the beer still, and that we can have for the different grades of alcohols. So in this procedure, many other byproducts will be formed. So the beer still, that is the steam distills, and then we can have the aldehyde the column where the byproducts like aldehydes and other, that will be removed. So that will be termed as the so that aldehydes, that will be sent, and the other product, that is fusel oil, that will be sent mainly for this the solvent, or that can send to the rectifying, and that can be stored. Then the alcohol which is the low concentration, that will come over here, and with the help of the anhydrous tail, or we can destructive the distillation, we can have the 100% ethanol, or by the azeotropic we can have the 95% of the ethanol, or we can have the denatured alcohol, which is 100% alcohol in this still. Then the whatever the remaining products or the waste which is forming, so that will send to the waste disposal or evaporator to produce the cattle feed or the fertilizer. So here the C, which is represent the condenser, then P is the partial condensation or deflagrameter, and H is the Prerequisite exchanger. So if you see the process again over here, then molasses, they will directly go for the fermentation after sterilizing or by diluting, that will produce the ethanol over here, and CO2 is scrubbed out. Then that will come to the beer still, and beer still, it will whatever the alcohol is there that will be sent for the aldehyde column, where aldehyde is removed by the distillation. Then the other byproduct, which is fusel oil, that will be removed over here. Then that will yield the ethanol, which is a purified one. So that will come in anhydrous still, which will give 100% ethanol. So here we are using the benzene for the extractive distillation. Then whatever the raw materials which are there, which you can send out, and then the ethanol, which is 95%, after the rectifying column we can store, or we can have the denatured alcohol, and then stripper, it will be stripped out and we can have the 100% ethanol. So generally what happens in distillation, the low boiling point, they will go up, whereas the higher boiling point, they will settle down. So here the high boiling point, generally it is the waste material, so that will be sent to the disposal or as a fertilizer. Then in the extractive distillation, what happens, benzene, which solubilizes the one component preferentially over other one, and it will form the component which is difficult to boil up. So that will lead to the bottoms, and the water which can be boiled off, and that we can remove over here. So the benzene is a good solvent for the production of the 100% ethanol by the extractive distillation. The main engineering problem over here is collection and storage of molasses. So the collection is generally from the sugar industry. Then storage is difficult because it will lead to the degradation of the sugar content into it. Then maintenance of sterile and specific yeast culture condition. So this is the difficult thing because the sterile environment is necessary, otherwise the nutrients will be contaminated. Then batch versus continuous. So continuous molasses dilution in the head end of the process and the continuous distillation are incorporated to save place, equipment and the operating cost. So continuous in this one is better. It will save the place. Also the equipment will be less in this case, and by this one we can have the overall operating cost less in this case. Then the waste disposal problem. If uneconomic to concentrate for cattle feed, must use tickling filters or activities such as anaerobic digestion to lower down the BOD before discharging to water. So biological oxidation demand should be low, otherwise it will pollute the natural source. So the waste disposal, if it is not of useful, then we have to go for the digestion to lower down the BOD, and when BOD comes to the desired level, then we can dispose in the natural the water. Then fuel economy in series of distillation, use of free heat exchanger. So here what we can use, the series distillation. So here what happens, the steam which is going from the first distillation column is sent to the other distillation. So the same steam is used. So if we are using this in continuous manner, then we can have the fuel economy and we can save the fuel. Then development of method to produce anhydrous alcohol from 95 alcohol as a top. So the various techniques which will lead to the 100% alcohol from 95% alcohol.